Good afternoon to all of you. So we are in the current phase of discussions looking at what is a typical certification scheme that makes use of the deductive process for failure analysis, which can evidently be an indication of the precise likelihood that a particular avionics system fails at a certain point, and that can in turn be transformed into a suitable level of the certification that an eventual uh, certifying agency would offer for a specific avionics system that has been developed and is likely to be deployed pervasively on board regular aircraft operations. Okay, so in that interest, we are looking at this particular element called the fault tree analysis, and the method to quantify the typical analysis process makes use of some expressions or formulae. Okay, so this primarily have an indication in terms of the probability of failure that can be ascribed to a specific avionics system. So we'll look at a few of this. The first one is the evident case for failure associated with a component that cannot be undone. Okay, or an event which cannot be revisited, because the event is like if it has indeed happened, there is no chance to adapt a corrective procedure for that. Okay, so in such a case, the probability of failure, okay, is given as an exponential term, which is 1 minus e to the minus lambda t. Okay, so lambda here is the number of times a particular component fails. Of course, because it's a rate, it is given as a certain number of failures over a duration of time. So it is the component failure rate. So the other one is capital T, which is the duration of time over which a factor had been contributing to this failure. Okay, so which means if there was an external parameter or an inherent feature in the component which had been acting over a course of time, leading to a certain number of components failing over the same extent of time, then the product of lambda and t as an exponential term, and 1 minus such an exponential term, will be an indication of the unrepairable state that the component would reach, or the avionics system or a specific service offered by such a system would indeed converge onto. Okay, so that's the failure probability. Next one is to do with a component that can indeed be serviced or repaired. Okay, so in which case you have another expression, which is the ratio of lambda t over 1 plus lambda t. So evidently you have some approximation that has gone into the earlier expression in order to arrive at this. So binomial series expansion is indeed relevant here, and that can in turn be approximated into a lambda t, which effectively is a product of the failure rate or the occurrence rate if it is an event, which is not in the interest of the avionics system. Okay, so primarily fault tree analysis considers the top event as the failure itself, okay, or the fault, depending on the context. Okay, and we had seen the difference between the two in one of the earlier sessions. So independent of that context, you have either a failure or a fault attributed to a component or an event, which in this case is a service offered by an avionics system. And the time taken to rectify that is indicated as the tau. Product of lambda and tau would result in a certain element of probability associated with a repairable or maintainable component which has undergone a failure. Okay. When it comes to the typical probability for a component itself, okay, so it is a constant and it is directly related to the number of such components that have been put into active use in an avionics system. So the probability is a constant element and it varies directly in terms of the numbers of such components which are used. So these are the typical quantifiable parameters that go into analyzing the nature of fault and how fault tree analysis can be invoked based on the probability number that is obtained as an outcome of all of these investigations. All right, so the fundamental attribute of probability is something which needs to be considered with an enhanced level of treatment given to it. Okay, so primarily probability or probabilistic uh, mathematical schemes are applied when there is a certain element of uncertainty in the overall process that is applied. Okay, so in this context, you have error and failures which are not very definitive in terms of their specifications. So you have uh, at the basic level two types of uncertainties which will need to be invoked in order to offer a certain enhanced understanding on the probability estimations that have to be obtained eventually in the component performances, okay, or the avionic system performance or the service rendered or the so-called event that is unfolding with the use of a certain avionic system. So the two broad divisions in this uncertainty are the uncertainty associated with modeling and the uncertainty associated with the parameterizing aspect. Okay, so let's take modeling uncertainties as the first case. So this is primarily taking into account the fact that the success and failure criteria are fundamentally an assumed entity, which means you would have the extremities of the performance reasonably well defined. Okay, so or if they are not precisely known, you make certain assumptions to start with in terms of what constitutes success, which means if it's a component which has been able to confidently perform operations or an avionic system which can be deployed with sufficient confidence in quite a cross section of aircrafts, wherein it is known to have a reliability associated with its performance, which means it has demonstrated its convincing ability over a certain extended duration of time, over a certain number of missions, okay, whichever be the case. So that is success. If it has failed to be of a convincing demonstration in terms of its performance characteristics, then you set a certain threshold for that and define anything lesser than that as a failure case. So the success and failure criterion are fundamentally defined. In the case unknown, you make a very wise assumption about it. Okay, so that's going into the uncertainty. So you are making an assumption and it is clearly not going to be an aspect of reality. So modeling uncertainty is going to consider aspects of success and failure in terms of a criterion that is assumed. Okay, next you have certain aspects which are very not so vital, okay, as contributions which could be excluded. So how do you define those? So in an avionic system, not all of them are going to be of paramount importance. So we had seen the criticality aspect in this regard a little while back associated with the flight control system, FCS. Okay, so how does one define criticality in three levels? Okay, so non-critical and essential aspects and so on. So in this respect, contributions which are non-critical would very likely be excluded. So such aspects also have a potential to bring themselves into a significant element of importance at some point in the performance of the avionic system, although to start with, these were assumed as non-critical. Okay, that's again a second aspect in the modeling uncertainty domain. Next is various independence assumptions that are made, okay, regarding the conditionalities under which the avionic system functions, their abilities to influence the overall performance, be it in software or hardware. In software side, you have certainly quite a bit of the operating system defined aspects, the hardware defined aspects, and the various intrusions and malicious attacks also. Okay, so all of this are considered as assumptions which are independent of the primary realization of the avionic system. Okay, so what are the independent assumptions which are defined in the overall understanding of the failure? So that constitutes the so-called modeling uncertainty. When you come to parameters which are contributing to uncertainty, that is the second of the two uncertainty factors. The first one is modeling, this other one is the parameters contributing to uncertainty. Okay, so these are fundamentally values in the data that are most likely not very precisely defined. Hence, there is a certain degree of uncertainty. So we had seen earlier on in this course how analog information is a real world entity, while the sampling brings it into the computing or digitized domain. So in the process of conversion from one to the other, there is certainly going to be a lot of information which is not considered because of the inadequate sampling that has been performed in order to convert the original data into digitized form. Okay, so this sampling errors, okay, this constitute a certain uh, non-exact definition of the actual values for the data. Okay, so that uncertainty is a typical example of the parameter uncertainty. In this context, it is the uncertainty in the data values. So a combination of these two contribute to a certain degree of deviation in the analysis process applied to estimate the probabilities, and that in turn influences the overall outcome of the fault tree analysis process. All right, if you have made a sufficient note of what has all been discussed regarding the uncertainty factors, let's go into the procedure of validating a fault tree analysis scheme. Okay, so what are the steps to be followed here? Fundamentally, select a lower order minimum cut set and validate that these are potential paths for failure. So you choose the very less numbers, even while minimum cut set defines only the least value. Choose even a subset of that in terms of performing a typical validation that will take it eventually to the top event, which is a failure case. Okay, so that is the step-by-step process that is adapted. Okay, obtain this minimum cut set for an intermediate fault and validate these selections as potential paths which can lead to the actual failure case itself. Okay, followed by that, obtain the successive paths and validate such selections as indeed the true successful paths which will lead to the top event of a failure case. Okay, so you have various intermediate steps that connect the basic events to the top event. So the basic events are fundamentally, if it is a hardware related element in avionics system, it is a component failure. Okay, and you have various subsystems which are assembled out of such components, and each of the subsystems and the relevant cases for failure of them will only ascribe the failure of that subsystem, which is an intermediate level, to a limited number of such components. So you'll need to really identify that minimum number and directly establish a connection between that and the immediate above level, which is an intermediate level of some hierarchy, some step in the hierarchy, and potentially take this analysis along a very promising pathway which will lead to the top event. So that is the way the analysis propagates, okay, all the way to the top. Followed by this, what you do is review the failure records and the typical hazard record reports in order to check the coverage of the fault tree. So to what extent is the overall failure completely retained within the focus of the entire gamut of analysis that has been performed, that takes the failure from the bottom and does a sort of deductive backward propagation study leading to the actual fault. So the failure records and the hazard reports need to be checked in order to assess the overall coverage that the fault tree is offering in terms of understanding the nature of failure. Followed by this is what is called as a sanity check on the very fundamental and important results and the probability results about which you are seeing right now. Okay, so the probability of failure has to be consistent with the nature of the analysis that is being pursued. So is there a one-to-one correspondence. So that is called as the sanity check. So it may be a highly analytical process without any bearing on the actuality of things. So that is where a sanity check will have to be performed, which will relate the important results to the probability derived estimations of the cases for failure as pursued using the fault tree analysis. So these are the methods that are adapted in order to validate the fault tree analysis. Up till this point, I was mentioning about the reverse process of understanding of a failure, to which a fault tree analysis is very well tuned. Okay, that being the case, there is also the possibility to take it out of such a context and look at its ability to perform in a typical case that involves design and development of an avionics system, wherein there are certain chances it can still be applied here. Okay, wherein you are now going to consider the FTA as a constructive exercise. Okay, for this, what are to be done? So the top level fault trees are fundamentally developed in this context of development and design, taking into account aspects such as the functional level, system level, and the subsystem level of understanding for which fault trees can be invoked. Functional level is when it is operational in its fullest extent as an avionics system ready to be deployed. So you can certainly take in elements which are fruitful in terms of the actual benefits and analysis process such as the FTA offers into the operational levels of an avionics system. So that is the functional attribute. So you can also do the same thing at the hardware realization level, where it is not part of an operating aircraft environment, wherein you have the system level and the subsystem levels of development that can be investigated. Okay, potentially leading to the product development. So eventually you'll have a concept and a realization of the product, at which point FTA will be a useful tool if it was used during the developmental phase also. Okay, so there are trade-offs that will need to be carried out in this context. Okay, so you'll need to identify alternative functional capabilities and alternative or redundancies associated with the system and the subsystem. So if you have a chance one of them potentially fails, you'll need a backup solution also. Such redundant implementation of the avionics is very distinctive in order to ensure a fail-safe operation, considering the criticality associated with avionics and aviation platforms. By and large, anything taking to the air is extremely important in terms of the mission that it is likely to carry out. Okay, so you cannot really afford a failure there. So that being the situation, you have to certainly ensure that if there is a potential for failure of a subsystem or a system, you have a backup possibility. There are instances of dual and multiple redundancies that are incorporated in various solutions used in avionics. Okay, and you'll see an example of that in the process of discussion of the data links or the data bus elements. Okay, so right now the trade-offs that are involved in the incorporation of redundancies and the possibilities for alternative functional capabilities, so that if a mainstream application of the avionics subsystem has indeed failed, you can potentially derive functionality from an adjacent avionics system. Okay, we have seen the example of this during the discussion of the LRM, line replaceable modules, wherein more than the case for face value of integration, you have extended levels of integration that can be incorporated that borrows functionality from adjacent subsystems. Okay, so that way there is still the possibility to retain it in a certain degree of operational state, and we had seen the operational states 1, 2, 3, 4, 5 in the flight control system. So such kinds of critical operational states can still be realized by borrowing spare functionality which is not being used by an adjacent avionics system, thereby enabling the case for reduced scales of functionality of fault or failure, and as a result, the so-called probabilities of failure are also going to be correspondingly less. Okay, so these kinds of functional capabilities, which can be alternatively defined from adjacent avionic systems, and the availability of straight and totally dedicated redundancy aspects, which means 1, 2, 3, 4 parallel implementations which can serve as backups. Okay, either as a spare resource or as a dedicated resource if you are able to identify avionic systems. That is indeed involving a case of trade-off, because you have to carry multiple units of the same type. Even during the design phase, you will need to include such aspects so that it can be used as a borrowed resource by an adjacent avionic system. So that goes in from the design and development phase onwards. So clearly, FTA can demonstrate its performance even during such a development and design aspect of the avionic system. Next comes the case for allocations in terms of the performance realization of the avionic systems. So how do you typically offer spare resources and identify allocations of such resources for adjacent avionic systems? Okay, system requirements translate into corresponding subsystem requirements of an adjacent avionic system. So if you have, for example, a processing power which is not fully utilized because that avionic system does not have a utilization during the specific phase of the mission. Maybe it is in a phase where some of the critical onboard electronics and software driving such electronics is not put into use for the time being. So in such case, these constitute the so-called subsystems, and what sort of requirements have to be placed on them so that they become vital system level requirements for another avionic system which will require such kinds of resources. Okay, during the specific operational aspect or the phase of the flight. So these kinds of subsystem requirements that translate into adjacent system requirements themselves is typically identified as an allocation aspect, and performance of such outcomes of allocations need to be investigated totally. In turn, if you look at the subsystems themselves, they will also have a certain requirement that they place on the components. Okay, component requirements translating into subsystem requirements, and subsystem requirements that translate into system requirements. How are allocations done? Which means you are going to carefully coordinate among the spare resource availability that can be invested into a vital functional attribute of an avionic system which is currently operational, considering the typical phase of flight in which it has to perform its role. Okay, so you have taxiing on the runway for aircrafts, the ascent or the takeoff part, the cruise phase, which is the level flight, then the descent or the landing part, and one more taxiing. So during each of these phases of operation of the aircraft in its flight mode, various avionic systems will be either switched on or completely turned off. Okay, so when it is turned off, you really are not using that, although it is still part of the aircraft. How better to deploy such resources in a more efficient manner? So that is where allocation lies. So component, subsystem, and system requirements are progressively redefined in order to attribute such aspects of allocation, and the performance is evaluated for the avionic system based on a careful and judicious allocation of spare resources that in turn can help avoid a case for the failure itself. Okay, as implementations in the form of a redundancy or as a spare capacity of a particular functional attribute of the avionic subsystem or a component for that matter. So these are some of the methods by which during the design and development phase itself you can incorporate such features, with the understanding that the FTA will lead to a certain probability of failure, and its ability to be serving as a tool for forecasting such failures can be used during the design and development phase onwards. So thereby the overall method of FTA, which had been primarily defined in failure space, can now operate in the success space, which can result in a very robust product development and its eventual implementation in aircraft systems. All right, so we are close to the concluding remarks regarding FTA anyway. So primarily, as the end of all of these activities that are performed, including the uh, visualization, which involves constructing the fault tree itself. At the end of all of this, you'll need to make a write-up of what was all pursued, okay, as part of the failure analysis or for the matter, the development in which FTA had been of utilization. So there has to be a clear line of communication established for this. So the understanding primarily can be derived by an agency or a person not associated with the intense levels of implementation, which was done possibly by a different group of people. So if they'll need to understand the entire process, it needs to be written down somewhere. Okay. So that is where you have the formal documentation of the system failure analysis coming into its own. Okay. So it is a structured tool for a what if analysis that has been fundamentally performed in the form of the FTA. It is a pictorial or visualized representation of the progress in the failure path that has led to an eventual avionics system failure. A failure diagram of the entire system that has to be maintained with the various system drawings that also go into it. And it also serves as a tool to extract information that can in turn be communicated to the very specific numbers of engineers, managers, and safety assessors, such as the certifying authorities and so on, so that the effective process of dissemination or the communication is in place as a terminal activity associated with the fault tree analysis method. So you need to generate the so-called formal documentation of the system failure analysis, including all of these aspects such as the drawings, the discussions related to the pathways of progress, how the analysis was pursued, what was the minimum cut set, which was the most appropriate one to choose, how did the propagation of the analysis for failure take place, how was it validated, what sort of a quantitative element had gone into its overall understanding, okay, such as the probability estimations and so on. Every one of this needs to be documented as part of the dissemination exercise. Okay, as a final comment, let's look at some of the important applications for fault tree analysis. The first and foremost one is the understanding of system failure and the factors that contribute to the failure. Okay. Next one is identifying the features in the design and potential weaknesses that can also exist or rather coexist as part of the design in the form of various features. So it is always functionality before form. Okay, so that is something you'll need to keep in mind when it comes to avionics system. It is not all uh, the aspect of the presentation, but it's the operationality which takes the front seat compared to the presentation. Okay, right. So the evaluation of various trade-offs is again one more aspect which can be identified as part of the application side. The prioritization of the contributions made by various factors to the focus or the so-called top event. Okay, so that is again an application side. Now you can compare among the various goals that have been set as part of the understanding of failure. So again, the identification of the typical top event is going to be a prime criterion here. Minimization of the failure probability despite the understanding that has been earlier identified, with every one of the elements of the fault tree if there has to be a minimization of this concept of probability. Okay, that is fundamental to the quantification of failures, what needs to be done. So that in you have an application for FTA coming into its own. Okay, then you have diagnosing the causes of a failure or of a typical incident in the case where originally you are going to define an aircraft performance or an avionics system performance as an event-free operation. Please make a note that an event-free operation in avionics system is considered as a successful operation, which means if you notice nothing, it is considered as successful. If something has been brought to the notice, it is very likely that it was a detrimental outcome that had taken place, which means it is a eventful operation. So you will want avionics system performances to be event-free, okay, or incident-free. That is effectively an indication of the reduced scale of failure attributed to an avionics system, and the diagnosing of the various causes of such failures or an incident is fundamental to the invoking of the fault tree analysis process. All right, after having gone through some of the procedural elements of certificability, now let's get back to the next of the parameters in the entities, and this is called as survivability. Okay, as the name indicates, it is a measure of the ability of an avionics system to remain in operational condition, okay, or to remain in a survivable mode. It is indeed a function of two separate parameters, which are again entities in their own right. So these are the susceptibility and the vulnerability. So let's look at each of these terms, because these two are going to be defining the entity called as the survivability. Okay, susceptibility is a measure of probability that an avionics system or an aircraft will be impacted by a specific nature of threat. Okay, so there is a factor of threat that is external or possibly which has been incorporated into the design, with the realization that at some point of time or at some phase during operation it will manifest. Okay, so with that understanding, when is it likely to happen and what is the probability that such an impact will render the avionics system as dysfunctional. Okay, so it is a measure of the probability that an avionics system will be impacted by a specific type of threat, okay, or a factor of detriment called as the threat in this context. The next factor is called as vulnerability. It is a measure of the probability that the typical damage to the avionics system will occur if there is a chance that it is impacted by a type of threat. Okay, what is the level of damage that can be sustained by an avionics system and the typical probability ascribed to such a damage on account of the impact that is being caused by a specific type of threat to the avionics system. So that's called as vulnerability. So this susceptibility and vulnerability together would be factors that will decide a particular entity called as the survivability concept. And as part of the scheme that is used to optimize the design, development, and operation of an avionics system, you also have the factor of cost. Okay, SWAP-C indicates size, weight, power, and also cost. Cost is an important attribute a highly costly kind of avionic system certainly has no chance against a cost-effective alternative solution. So given that possibility, there are various elements of cost also to uh, take into account. Okay, so these come under the factor called as the life cycle cost, LCC. Okay, also called as the cost of ownership. So if there is somebody who has paid for it, it directly translates into the so-called cost of ownership. It is within its ambit having quite a bit of expense heads identified with it, okay, or the cost heads. The life cycle cost has so many attributes within it. So it fundamentally deals with economic measures that are needed to evaluate the avionics architecture. The life cycle cost or the cost of ownership includes cost factors in terms of the varied items such as the acquisition of spare parts, okay, replacement parts which can be used in place of a dysfunctional avionics system, a subsystem or a component. The cost involved with transportation of such a part, the cost involved with storage and warehousing of the part which can be made use of when there is a need. So until that time it will need to be uh, located in a carefully climate controlled situation. Okay, so that is the storage concept. Then requirements as regards training for the crew and the maintenance personnel who will need to be paid for that. The development of hardware and the testing of the hardware again is an important aspect of the cost that goes into the life cycle cost. And the life cycle of an avionic system starts from the concept and goes all the way till decommissioning, which means it is considered as obsolete and has to be thrown away. Okay, so that's a typical case for decommissioning. It cannot be literally thrown away in that sense. You have a procedure for completely destroying it. Okay, so that it is no more considered as existent at all. So that decommissioning phase is the terminal aspect, starting from what is called as a concept phase. So this entire scheme is called as a life cycle of a product. So during each of the phases within this life cycle, you have some amount of cost that is incurred, starting with training the crew, deployment of the component, identifying spare parts, keeping spare parts safe in a condition where it can be used when there is a need, requirements for transportation to bring that particular part into a integration facility for the avionics system, because several components are manufactured by various types of vendors or sold by various types of vendors. This all have to be brought to one location where it is integrated. Okay, so transportation costs are certainly involved there. Then you have the development of hardware, the upgrades and maintenance that will need to be done. Additionally, with use of the product, its value reduces. Okay, so that's called as depreciation. There are also cases with avionic systems which appreciate in value. So you have a case for both appreciation and depreciation in the product with its utilization over a course of time or with aging. So that also needs to be considered. And if it has been owned as part of a loan that has been taken, okay, so which means it has been on borrowed money that this product is currently in operation, you certainly will have to consider the factor of interest that goes into the payment part. So every one of this that you consider with the procurement and deployment and operation of an avionics system has a specific aspect of money or economy identified. It is a fiscally taxing kind of a situation, okay, with the incorporation of an avionics system. So rating in terms of the cost factor is also an important attribute in the overall scheme of deployment of an avionics system. Okay, coming to the case of risks that are involved, which can potentially affect the performance of an avionics system. Okay, so risk is primarily defined as the amount of failure or the potential level of drawbacks in the actual design and implementation associated with an avionics system. So overcoming the risk by use of latest technology and a failure-proof scheme in operation that can overcome both the developmental and long-term technological risks are fundamental to the choice and operation of an avionics system. So there are likelihoods that a significant amount of failures can take place. And what is the level of survivability, which is in turn defined by two additional parameters such as the susceptibility and the vulnerability, will in turn manifest itself in the form of the specific drawbacks associated with the particular design, concept, and realization of an avionics system. And use of technology at various levels has to be done in a very carefully calibrated manner so that you have the possibility to retain it with a reduced level of less risk with operating the avionics platform. Okay. Next comes the parameter called as the weight and power issue. Okay. The minimization of weight and the minimization of the power requirements during the operation or deployment of an avionics system are fundamental concepts as part of the avionics system design itself. So the design of an aircraft electronics driven solution must be primarily of less weight, and it should also consume less amount of power. And this is primarily enabled through various assisting technologies such as data links and data buses, along with advancements that have taken place at the component level in terms of the superior levels of semiconductor material that is available, the higher levels of packaging factors that have gone into the realization of the avionics implementations, okay, and the connectivity options that exist, which are converging into the sub 2.5 nanometer scale in terms of the actual electronics and component specifications. Okay, so your evidence of all of this would be in the form of the multi-chip modules or hybrid ICs that we spoke about in an earlier discussion, and the incorporation of connectivity solutions in the form of data buses or data links. Okay, wired and wire-free methods for connectivity. Both of this would together constitute a means by which you can save on adding more and more of transmission lines that are used to interface among the various avionics systems in order to generate an integrated solution of avionics. Okay, so that can be avoided by a more rational use of the connectivity solutions and the deployment of components which are having a higher density of logic devices packaged into them. Okay, so by this means there is the eventual enabling of a small form factor device which does not weigh too much, neither does it consume quite a high level of power in order to make it an operational aircraft technology that is primarily driven by electronics. All right, so in the next session for this course, we'll be looking at the maintainability and the reliability aspect as the final utility parameters that are used to rate the performance of aircraft electronics. During the remaining time that is available today, if there are any clarifications that you will have, this can be cleared up, and you can pose questions related to that, to what we had discussed today.